Welcome back to another video. All right, so in this section, we're in 7.2. We are talking about the sum and difference formulas for the trigonometric functions. Okay, so here we're going to try to work out example 4. So let's zoom in a tiny bit so we can read this. It says, here are the directions. Write, and let's highlight this. Huh. Okay, my highlighter doesn't work. I apologize. Let's maybe switch colors then. Okay, so here's our goal. Our goal is to write sine of, now all of this is going to be in 1 mega parentheses, sine of cosine inverse of x plus tangent inverse of y. And our goal is to do it by writing this as an equivalent algebraic expression using only x and y. So, very good problem. Tag this as a GTQ, since this is an extremely important skill in calculus. Okay, so what we have. Now, I added those green parentheses. I hope you could see them. It might be a little hard to read. But the key is we have sine, and then we have two inverse trig functions. Now remember, what is an inverse trig function? Very quickly, just to remind you and get this context straight. If we think about a quick little unit circle, and if we think about the terminal point, then we have an x and a y coordinate. Well, if we evaluate sine of, and let's think of this as like a, I'm not going to call it t, but let's think of it as an angle theta. So if we have an angle theta in radians, that tells us a terminal point xy. Now cosine of theta would be the x-coordinate, and sine of theta would be the y-coordinate. The inverse trig functions just basically undo that. So if we start with, a number, like let's say x, which is down here. So for a number x, if we want to do cosine inverse, it's basically saying, well, what angle theta do we need so that I get x? So it's kind of going backwards, right? And then for tangent inverse of y, it's saying, okay, if I have a y-coordinate, if I want to do tangent inverse, what angle will land me at that value? So what that does for us is it does the following. The key insight for this problem is as follows. There's a couple key insights. All right. First, what we're going to do is let's say number 1. We're going to pick an angle, and I'm going to call it theta, and we're going to set that equal to be cosine inverse of x. Okay, and number 2 is we're going to set another angle, so we can use, if we're using theta, typically I'll use phi, and I like to write it either like that. Sometimes you'll see me write it like this. They're the same symbol, phi, they're just kind of, one's cursive, one's not, that's basically it. But let me use this one. This one's a little bit more easy to remember. Let's set this one for tangent inverse of y. Okay. With that, we can rewrite sine of cosine inverse of x plus tangent inverse of y. We can just rewrite this, again, because we're defining theta and phi using these identities, we can write this as sine of theta plus phi. Just to kind of simplify the notation here. All right. So I have some addition and subtraction formulas covered up here. Let's get rid of some of these. So if I uncover that one, and this one, and if you look at these, which ones do we need? Looks like, this is funky. I don't know why the highlighting is not working. Weird. Okay, let's highlight it like this. maybe use a blue. So we want the sum formula for sine. Okay, so let's just apply it. We have sine of theta and phi. Here it's written in terms of s and t, but that's no problem. Let's follow the formula. First piece we have is, so these are our first two pieces. So let's see, we're going to get sine of the first piece, sine of theta, cosine of the second angle, which is going to be phi. Okay, so instead of s and t, we're using theta and phi. All right. Next, we have plus. So we'll add a plus here. And next, we go cosine of the first angle, sine of the second angle. So then we'll have cosine of theta, sine of phi. So, good. We've written this, and now we have a different expression. Oops, I'm sorry, I'm covering my equation. All right, so we've got sine of cosine inverse of x plus tangent of inverse of y, and now we have a new expression that we're looking at. So what do we do from here? Let's reread the directions of the problem. So what were the problem? Asking to write this as an algebraic expression using x and y. We haven't done that yet. Our expression uses theta and phi. So somehow x and y need to get brought into this. So time for some more key ideas. Okay, next what we're going to do is we're going to rewrite the theta equals cosine inverse of x and phi equals tangent inverse. We're going to rewrite those in an equivalent form as follows. So thinking of this equation, we can write that as cosine theta equals x. Why is that true? Let's think about that. Remember, if we apply cosine to both sides of the equation, cosine theta is what we get on the left, and then on the right we have cosine with cosine inverse, which will cancel each other out, giving us just x. Okay, if we do the same thing for phi, what would we get? We'd get tangent of phi equals y. All right. What's our next key insight? So that's getting us in the right direction. The next key insight is we are actually going to write this as fractions. So we are going to write this as x divided by 1 and y divided by 1. Now it seems like a silly thing to do since that's the same thing, but you'll see why in just a second. Third key insight, or the next key insight, is we want to draw some triangles. Okay, and let's say this one's 5, draw triangles. What do I mean by that? So we're going to take these two equations, cosine theta equals x over 1, and tangent of phi equals y over 1, and draw two hypothetical triangles. So let's do that next. So let's draw a triangle, a right triangle I should say, and then I'm going to really exaggerate that they're different by just making them look a little weirder. And I always like drawing my angles on this side, so I'm going to draw them like that. Two different triangles. All right, so now that we've got that, we have to remember, okay, cosine of theta, I've got a triangle with theta in this corner. Cosine of theta is the adjacent side divided by the hypotenuse. Now, I have an equation here where I have an x divided by 1. So what I'm going to do is the adjacent side is going to have length x, and the hypotenuse side is going to have length 1. Okay, so that is how we basically translate this equation into a triangle. Okay, we can do the same trick with our next equation using tangent. Tangent is opposite divided by adjacent, so opposite is y, adjacent is 1, so the phi is sticking out, so let me make that a 1 on the adjacent side. Okay, great. From here, you can see where we're going, because notice that looking back to what we're working with over here, we have a sine theta, cosine phi, cosine theta, sine phi. Well, now that we have some triangles, we can actually use the triangles to figure out sine of theta, cosine phi, and basically all of these. So let's go through them one by one. First piece that we need is we need sine theta. Sine theta, since we're dealing with theta, is going to work with this triangle. And for sine, we're going to need this missing piece. Okay? So without even trying to, before I continue back into the equation up there, let's actually find that missing piece. And while we're at it, we have a missing piece here that we might or might not need. Usually you'll need all of them, so you might as well just continue with the triangles before we move on. So if we want to figure this out, let's call it O for opposite, and let's call this H for hypotenuse. So if I want to figure out what O is, I can use the Pythagorean theorem. Always keep in mind where your right angle is and where your hypotenuse is. So we can write this as x squared plus O squared equals 1 squared. And our goal is to find O. So I'm going to keep the O squared on this side. 1 squared is 1, but I can subtract x squared from both sides. And then I can do O is equal to plus or minus the square root of 1 minus x squared. Now, what do we do? Well, remember, this is a triangle. A triangle has lengths of sides. And the length of a side is a positive number. So I'm actually going to take a positive square root here because of that reasoning. So there's our O. Can do the same thing for the next problem. I'm going to go a little quicker and maybe not explain it, but we have, using the Pythagorean theorem, 1 squared plus y squared equals to h squared. Since we're solving for h, we can write this as 1 plus y squared square root plus or minus h. Same thinking. Pick the positive. Now we know that our h is going to be square root of 1 plus y squared. So we've got all of our sides of our triangles. Now comes the magic. So let me hide those calculations, but I do want to leave this up. So we've got our triangle. We've got all three sides accounted for, and now we just go one by one. Whoa. Okay. So sine of theta, that's this first piece. That means go to our theta triangle. Sine is going to be opposite divided by hypotenuse, which means we can write opposite is the square root of 1 minus x squared divided by hypotenuse, 1. And I'm going to use this color chalk for each of these. All right, so next one up is cosine of phi. Well, here's our phi triangle. Cosine is going to be adjacent divided by hypotenuse. So let's write that out. Adjacent divided by hypotenuse. Sorry, I'm going to move this real quick. Okay. Next one, what's the next problem we're going to work on? Cosine of theta. So back to theta means, okay, cosine of theta, back to this triangle, but now we're doing cosine. Cosine of theta, what would we get? Adjacent divided by hypotenuse, so we get x over 1. Last one, sine of phi. Phi means we go to this triangle, and then what's sine? Sine is going to be opposite over hypotenuse. So there we have it. That is where we want to end up. Now, let's see, where should I continue this? It says simplify, write an algebraic expression. So I pretty much think we're done. I'm actually going to copy it and just let's write one more step. Copy that. Let's add a new page here. Not much more to do, but let's just simplify our work here. Okay, so as we look at these expressions, we've got this piece, and not much we can do, but why don't we just write it as a single fraction? Now, because we have x's and y's, they're not going to mix together, so basically that's all we can do. Then we have plus, looking at the second two pieces, multiply the numerators, multiply the denominators. Pretty much done. Now, in terms of algebraically simplifying it, if you box this, you'll get full credit. I'm pretty happy with this. One thing that's kind of nice that we can add at the end is we can notice that they both have the same denominator. They both have square root of 1 plus y squared. So what's kind of nice is if we have the same denominator is why don't we just write these two fractions added together. So we can write a final answer like this. And I'm actually going to do this trick where I'm actually going to write this one first, just because it doesn't have the square root. So you usually write the simpler piece first. You don't have to. You can keep them in the other order. But it's always kind of good to put the square roots at the end, since it doesn't confuse people when they read it that like, oh, hey, does the square root keep going? Is the square root over the entire thing? Or, you know, if you want to avoid the confusion, you put this little extra stick at the end of the square root to indicate, okay, the square root symbol ends at just this piece. There you have it. There is our example from 7.2. I think this example is really, really important. So it introduced a few key tricks. Let's go through them. Okay. Number one, the trick was to write basically these equations here. So basically, call that theta and call this phi. You can call them anything you want. You don't have to use theta and phi. You can use alpha and beta. You can use s and t, whatever. Just you can't use x and y since those are already used. Next key insight was to basically rewrite the expression using the theta and phi that we just defined. Use your trig identity, in this case the sum rule, to expand it. And once we have these, we basically go back to these definitions of theta and phi, and because they had the inverse trig functions, well, we can rewrite them in the other way, where you basically move the tangent inverse to the other side of the equation. And these are just as important. They're basically the same info as before, but what we have here is a new way to look at it, and the reason why they're important is, well, those lead us to triangles. And once we have these triangles, it's game over. Because basically, using SOHCAHTOA, we can find all of the pieces in this expression, and then we just go in and substitute them one by one. So it's a lot of steps, but it's such an important problem, and it really brings in these really key insights. All right, so that's our example. Lovely, lovely problem. Make sure you study this one and similar ones like it. I tagged it as a GTQ, so you can almost bet that you'll have something similar on the test. All right, hope you enjoyed this lesson. Have a great day.